I'd like to welcome everybody to this final IMS stream session for today, and that's the final IMS presentation for the set of presentations we've had for this virtual conference. And this is going to be an overview and use and best practice for IMS data entry databases with the SDEP portion and SDEP segment type. So there's going to be good explanations on all of those things which you ever wanted to know about the FastPath database type, which are obviously very special for IMS. And I'm delighted to say we've got Anshul Agrali from BMC Software to take this session, and he's been in BMC for he certainly worked for over 11 years on mainframe programming systems and applications, and then within BMC is working on the BMC software since 2016 as product developer for the FastPath utility. So he really knows his stuff. And so what I'd like to just say is, for anybody that wants to ask a question, then I will disable the all mute. So it basically means if you want to verbally ask a question, then please unmute yourself and ask that question, and Anshul will be happy to try and fill that question during the foils presentation. So without further ado, I'll hand over to Anshul for this session.
Okay, thanks, Tom. And let me know when you can see my screen.
Yes, we can see that perfectly.
Okay, so myself, Anshul Agrawal, I'm from BMC Software R&D team, and today we are here to discuss about one of the special database of IMS, that is FastPath database. And within the FastPath database, there is a very special segment type called SDEP, which is sequential dependent segments. So this session is going to be pretty deep, talking about the different concepts of the SDEPs and the best practices. So it is possible that some of this stuff may be overwhelming. So I would request you to bear with me. I will try to explain as much as I can, and you can stop me anytime, and I can be happy to answer your queries just at the same time. Okay. So let's talk about the agenda. What are the things we are going to cover in today's session? So we'll start with the basic overview of different parts of the FastPath area. Then we are going to cover the overview of SDEP segments. We are going to talk about bits and bytes of SDEP segment types. What are the logical and physical boundaries of the SDEP segments? Then pretty important concept of SDEP, which is wrapping and the unwrapping of SDEP section of the FastPath database. Then couple of special utilities which IBM provides with the SDEP, which is scan and delete utilities. SDEP in a sharing environment, which was introduced from IMS 6.1, which completely changed the way SDEP segments are worked in a sharing environments. Then we'll talk about SDEP buffers and the packages, which is pre-allocated SDEP CIs. And then we'll talk about SDEP physical quit CI processing, and also SDEP marker segments. And in the end, we are going to talk about a special feature which was added in IMS 14, which talks about automatic SDEP buffer management. So we'll start with the basic, we'll build it up, and then we'll go to some of the advanced topic. And we'll do that, all of that in next 1 hour. Okay, so DEDB consists of 4 different parts. One is the root addressable area, we call it RAA. One is the dependent overflow area, we call DOVF. One is the independent overflow area, which is called IOVF. And the last one, and not the least, is the SDEP, which is sequential dependent part. And this part is very unique to IMS FastPath database. Any other IMS database from the full function side of the house, they do not have this special dependent segment. And this is something for, you can say, very VIP kind of processing in the IMS FastPath database. We'll talk about it with some analogy. Okay, so you might have seen this figure in some other presentation from someone else. So this is nothing but a single VSAM ESTS dataset. And when we talk about VSEM dataset, it is nothing but a collection of control intervals. But when you lay out a certain structure on that VSEM, and when that certain structure looks like this structure, then IMS understand that, okay, this is a IMS FastPath DDB dataset. So let's take an example of a definition. So maybe I'll turn on the pointer. So this is the parameter where the CI size is 4K, UOW parameter is 9,3, and root parameter is 14,4. So when you say root parameter is 14,4, it means we are talking about 10 base UOWs from here to here, and we are talking about 4 overflow UOWs, which is from here to here. And then within the base UOWs, the CIs are divided as 9,3, which is 6 and 3. So 6 are RAA CIs and 3 are DOVF CIs. And there are 10 such base UOW CIs. So, and then you have one reorg UOW and then one very special section, which is called SDEP CI. So let's talk about this and consider this as a parking lot, okay? And lot of cars are coming which are supposed to be parked in some space in this parking lot. So we are distributing the cars based on their number, which is there on the number plate. So we will look at the number, and there is a special component in IMS called randomizer. So randomizer will take the number on the number plate as input, and it will tell you in which particular parking slot that particular car should be parked. So let's say we are talking about 3 states. One is Yukon, one is California, and one is New York. So if there is a car which is coming from a New York, it might have a certain number, and that number might translate to go into, let's say, UOW number 2 and RA number 4 in this particular section. And more cars are coming from New York, and they are occupying the space in this UOW number 2. And once all these 6 RACIs are full, then more cars in the same from the same state will be placed in this DOVFCIs, which is just an extension of this RACIs. So later on, all the cars which are coming from the New York, they will be placed in this 3 DOVFCIs. Now let's say this UOW number 2 is full, and now more and more cars are coming from New York. Then it is possible that we have a common section which gets allocated to the cars which are coming from New York. So there will be certain parking slots from this IOVF CIs which gets allocated to UOW number 2, which was dedicated for New York. So in this way, you can think of it as a parking lot, and your number on the number plate is basically the root key of the segment, which goes to the randomizer, and randomizer will tell you, okay, in which particular area your segment should reside. Okay, so that is for the normal cars, but we have a special or a dedicated section or a parking which is called SDEP CIs. So for all the VIPs or VVIPs, your cars will directly be parked in this SDEP section for the fast entry and the fast exit. So for all the segments where you want fast insertions and retrievals for your journaling applications, you are going to use something called SDEP, which is directly linked with the root segment. So you will have a root segment which will point to the SDEP segment, which will directly be inserted in this special parking slot. And from that, we have a couple of special utilities called SDEP scan and delete, which will scan the segments into a sequential file, use it into the downstream processing, and then you do the delete, which will logically delete the SDEP segments in this SDEP plant. So I hope this analogy is something which will make things very clear in terms of how IMS is going to place the segments based on the kind of updates IMS is going to receive. So again, SDEP is kind of a special parking area, which is used for very fast insertion and exit from the IMS updates perspective. Okay. Okay, let's talk about these SDEP segments, because this session is all about SDEP segments. So they are always stored in the order of entry. So they basically follow last in and first out. So you store it, and the segment will be stored under the root. The next segment will again stored under the same root, and that will point to the previous SDEP segments. and they will be intermixed in the STEP portion. So there is a possibility that multiple applications might be inserting the segment under different routes, and they might be intermixed in the same STEP section in the STEP land. So that is totally perfect and acceptable to IMS. As I mentioned earlier, it is used for fast inserts and retrieval. You can use the get next parent backward sequential program, and it will give you the backward sequential order of the segments in your sequential file. Then couple of special utilities, scan and delete, which will scan all your STEP segments into the sequential file. Use that file for your audit purpose or the downstream processing, and then do the delete, which will simply resets the pointer from the logical begin to logical end. We'll talk about the logical begin and end. And obviously no modifications are allowed. You can only do the insertions and delete by using the utility. You cannot basically update or replace the STEP segments. They are used for data collection, journaling, or auditing applications. Let's say on a Monday morning, there is a debit transaction hit on your saving account, and on the Tuesday morning you do the withdrawal and you want to journal that event. So for those kind of application, step segments are the perfect example. Okay, so let's talk about the S-step pointers, which is a very different pointers than compared to some other segment pointers, because they are 8 byte in length. So the first 4 byte is the cycle count, and the next 4 byte is the RBA, and they are formatted as 8 bytes. So the first 4 byte is the binary count of the number of times S-step portion has wrapped. So when we look at the picture and the step portion in little detail, we'll talk about what the wrapping and the unwrapping means in terms of the step segments. And then the 4 byte is just the relative byte address within the VSEM where your step segment is residing. There are a couple of very important pointers. There is a root segment which has the step first pointer, and then there is one pointer in the step segment which is step next pointer. So basically how it happens is, let's say there is no segment in the step portion and you are inserting the first step segment under a particular route. So that root segment will have a step first pointer which will point to the step segment, and that step segment will have a next pointer which will basically point to a null. Then you will insert the next step segment, which will be inserted in between the root segment and the step segment. So now the root segment will point to the second step segment, which you just inserted after the first. And then that second step segment will point to the first step segments. So always the step segments points to the previously step segment inserted under the same root. Then you have a very couple of important RBAs in the DMAC block, which is called logical begin and logical end. So within your S-step section, which is your physical start of the S-step and end of area, there is something called logical begin and logical end where all your active step segments reside. So there is a pointer or an RBA in DMAC, which is called DMAC XWell, which is pointer to the oldest step segment in the area. So that is basically a step logical begin. Then there is DMAC X NXTS, which is the position for the next step segment to be inserted, and that is something called logical end. And all the segments which does not lie within this two pointers are either called null pointers, or they are considered to be invalid. So where all the valid pointers basically fall between the logical begin and logical end. Okay, let's talk about the bits and bytes of the S-step segment. So you can think of this diagram as the S-step segment format. So the very first byte is the segment code, which will have the segment code for the S-step segment. The next byte is the unused byte, and then the next 8 byte are the S-step pointer, which is the S-step next pointer, which is present in the S-step segment, which is pointing to the S-step segment inserted under the same route, just preceding that S-step segment. Then you have the data and the length, and in the end you have the timestamp. And the timestamp is nothing but the time at which the S-step segment is inserted into the data. That field is something which was added from IMS 6.1 when the S-step data sharing concept was introduced. Because by that time there could be multiple IMS, they might be inserting the S-step segment from different sharing partners, and in that case they will have a timestamp, and they will also have the name of the IMS which is doing the inserts. Then let's look at the STEP CI. There are different flags which has a meaning. So if this flag is 01, which it says the timestamp exists, and if this flag is 04, it says STEP CI is full. There is a possibility that you might have a very old database which is before IMS 6.1, and it is possible that those STEP segments might not have the STEP timestamp. In that case, this flag will not be set. But over the period of time, after doing certain maintenance, I think most of those databases which used to have the STEP segments before IMS 6.1, which is I think almost 10 years old now, has already been translated to all the STEP segments which now has a timestamp. So that thing is already being taken care over last several years. Let's move on to the next slide, and let's look at this STEP portion. So the diagram that we have seen on the third slide, where we talked about the DMAC, the RA, DOVF, and the IOVF, reorg UOW, and in the end, we talked about the STEP plan, which is the special parking slot for the VIPs and VVIPs. So this is the starting physical start of the STEP, which is called DMAC FSEQ. So in DMAC, you have a pointer which points to the physical starting of your STEP. So there will be an RBA value in the DMAC. Then you will have the end of area, which is DMAC FPAD. And within the physical start and the physical end of the STEP, there is something called logical begin and logical end. So all your active STEP segments are lying between this logical begin and logical end. So this points to an STEP segment, which is the oldest STEP segment in this STEP portion. And this logical end is basic. This pointer is more somewhere here. And it is pointing to the STEP segment where the next, it is pointing to an RBA where the next STEP segments can be inserted. So what happens is, this is your first STEP segment and this is your last STEP segment. And if you insert more STEP segment, this pointer will start moving from here, and it will eventually come to the end of area. And then after that, if you start inserting more and more STEP segments, your STEP portion will be wrapped and your STEP segment will start getting inserted from here. So in that case, your logical end will come somewhere here in the top, so that your logical end RBA would be smaller in number or would be less than the logical begin. So that is one way to identify if your logical end is RBA is less than the logical begin RBA and your cycle counts are not same, then you can say that your STEP segments are wrapped. So this is the first STEP segment, this is the last STEP segment, and as and when you are inserting more STEP segment, this pointer is moving, which will eventually come to DMAC FPAD end of area. And then after that, if you insert more STEP segment, it will start inserting the STEP segments from here, and your logical end will be lesser than the logical begin, because here the logical end is always greater than logical begin if your STEPs are not trapped. But when it will be wrapped, your STEP logical end would be smaller than the logical begin. And eventually when when the logical end reaches here, then your STEP section is full and you will start getting the FS status code. So in the very end, we are going to see a demo of maybe 4 to 5 minutes where we will see how STEP segments are wrapped when we are inserting the STEP segments. Okay, so I think this is the example where the STEP segments are wrapped. So this is the physical start of your STEP section. This is the end of area. And this is the logical begin. So the cycle count is N here. This is the first STEP segment. This is the STEP segment somewhere in the middle. And then the more STEP segments are lying in the upper section from here to here. So here you have a logical end, which is having the less RBA compared to logical begin. And when that happens, and when the cycle count does not match, this is having a cycle count of N, and this is having a cycle count of N plus 1. And this N is nothing but the number of times STEP segments are wrapped. So you can easily determine if your STEPs are wrapped or they are in unwrapped situation to begin with. Okay, let's talk about the STEP processing and the STEP scan and delete utilities. So let's talk about the application DLI calls. So you can do the get next read on the STEP segments under a root. You can do the insert, new insert on STEP segment under a root. Replace calls are not allowed, delete calls are not allowed. So this is something we've already talked about. You can read the segments, you can insert the segments, you cannot replace and delete. When you insert the STEP segment, it logically advances the STEP logical begin, as we have seen in the previous slide. So this is the logical end, and when you insert more STEP segment, this logical end will move further. So this is what it tells, logically advances the STEP logical end, and segments are essentially stored in the chronological sequence. When you are deleting a route to which all the STEP segments are tied, it leaves those STEP segments as orphans. And delete, if you have defined delete cascade on the DBD, it is not going to delete the STEP segments. So STEP segments will be there residing physically, but logically they do not exist because you have deleted the root segments, and those STEP segments become the orphans. Okay, so we were talking about two special utilities, that is STEP scan utility and the STEP delete utility. So if you go back to this diagram, there is something, you have inserted the SDEP segments from here to here. And then once you are ready, you will use something called STEP scan utility, which will scan all the STEP segments from logical begin to logical end, and it will store that data into a sequential file, which again you will feed it to some downstream processing or application. And then you will run the delete utility, which will basically reset this logical begin to the same RBA, which is being pointed by the logical end. So this is how the logical begin and STEP scan and delete utility works. So the STEP scan utility is called DBF UMSC0, which extract the STEP segment data into a sequential file. It reads from the STEP logical begin to logical end, and it remember where it has stopped. And when you run the STEP delete utility, which is DBF UMDL0, it deletes the STEP segment, which is simply resetting the STEP logical to begin to the STEP logical end, or probably the end of scan. In certain cases, you might not be scanning till the end of your logical end. So this diagram is going to depict that scenario. So you have the STEP physical, you have the end of area, you have the STEP logical begin, you have the STEP logical end. So this is how your STEP portion looks like before scan and delete utility. But once you run the step scan and delete, it will scan all the data from here to here in a sequential file. And once that is stored in a safe place, you will run the delete utility, which will simply reset this pointer to the logical end, and you now have ample space to do more and more inserts. Okay, so that was about step scan and delete utility. I will take a pause here just in case if anybody has any question which I need to clarify. Otherwise, I'll move on to the step sharing concepts.
I've just got a quick question, Anshul. Just sometimes people put application markers in there for the end logical for applications. So sometimes that logical beginning and logical end, sometimes it might be up to an application marker that will scan off, not necessarily the logical beginning, logical end, but that's, you know, an enhancement that some applications can do. But often applications in different shops will do that logical beginning, logical end, and scan between the lot, like you say.
Right. So there is a special concept called step marker segments, and we are going to talk about that step marker segments in next few slides. So in that case, you might be inserting under a root, maybe on some special field, let's say maybe the time of the day, or some kind of special field. And in that case, you might want to scan using some special parameters in the scan utility, which is called start root and stop root, to scan between two markers. So it is not always necessarily that customers will always scan between logical and begin and end. But generally in most of the cases that might be the reality. But it again depends from one shop to the other, and depends on the application, how they are processing or extracting the step segments.
Great, thanks for that.
Okay. Okay, let's talk about STEP sharing. So as I mentioned, from IMS 6.1 and above, each that has completely changed how STEP segments used to work, because in single IMS, there is not much complexity involved related to STEP segments. But when we are sharing the STEP portion in a multiple sharing partners, things get very complicated. So IMS introduced this concept of step sharing from IMS 6.1 and above. And in that case, each sharing partners pre-allocates a step blocks for its own private use. And we call those CIs packages, which is pre-allocated step CIs to a particular IMS. And those CIs are basically allocated at the starting of the logical end. So you will have the logical begin and logical end. And from the logical end, you might have certain set of CIs which is allocated to IMS1, and certain set of CIs which is allocated to IMS2, and certain set of CIs which is allocated to IMS3. And your logical end is moved to that new position where all those packages are allocated. And your step blocks are hardened as they are filled by the sharing partners. So one of the very unique feature in the step segments and how it gains speed is they are not written to DAST or hardened to DAST when the segments are committed. They are only written to DAST when the blocks are full. When these packages are full, then only they are written to DAST. And the advantage of doing is that you have a block, and there are segments from different application threads which are committing step segments in that block, and you're taking that block together and doing all that IO once. So basically you are saving a lot on the IO, because you are not doing IO on every step commits. You are doing only a single IO for multiple step commits, and that's how step segments IO gain speed, because the IOs number of IOs are less, and they are done for a basically set of different step segments commits. And when the step blocks pre-allocated blocks are filled, the sharing partner will keep allocating more and more step blocks. Although doing this poses certain challenges, which we are going to talk in little later part of the presentation, how that challenge causes problem in terms of losing the step space, and what are the best practices to overcome those challenges. Okay, so what are the things that has changed in the step sharing? So step segments are no longer in the chronological sequence. So there is something new called step logical begin timestamp, which is the timestamp for the oldest step segments inserted in the area. So this is something which is introduced with IMS 6 with the step segment, and timestamp is appended to the end of every step segment occurrence. So all the segment which has a timestamp which is less than the logical begin timestamp. So logical begin timestamp is that timestamp which belongs to the oldest step segment in the area. So if there is any step segment whose timestamp is even less than that oldest step segment, then we are consider that that segment is logically deleted. And how step scan utility is going to differ its behavior is it is going to read from the step logical begin to logical end, which will include the pre-allocated step CIs to different sharing partners. It will sort the extracted record into time sequence, and then it remembers the RBA and the time when it is stopped. And then when you run the delete utility, it will reset the logical begin to the end of the scan, and then it will reset the logical begin timestamp to the end of scan, because once you have deleted, basically there is a possibility that it might not have any step segment, but if you have stopped at somewhere, then it will point to the timestamp of that particular segment where it is stopped. So the logical begin timestamp will be the timestamp of the oldest step segment, which will remain in your step section. As I mentioned, the step buffers and packages. So step segments are returned to online step buffers and returned to DASD when the buffers are full and not when the update is committed. So as I have already mentioned, step utilizes this performance gain of doing a single IO for multiple step commits from different application thread. Although there are some challenges of doing that or gaining that advantage. Let's consider that there is an STEP block or a PACI pre-allocated STEP CIs where the STEP segments are inserted from the multiple application thread, and it is possible that your block is full, okay, and all those STEP segments are returned to DASD. But it is possible that, let's say, 5 applications are doing STEP insert, but only 2 of them have committed the STEP segments. The 3 application threads have not committed the STEP segments. In that case, uncommitted STEP segments get returned to DASD. And it is also possible that those 3 application threads might abort the STEP segment. They will not do the commit. So there is a possibility of those aborted segments get returned to DASD as well. So in a sharing environment, there is a high possibility that you might get the aborted STEP segments or uncommitted STEP segments, or which will basically occupy some of the storage sections in your STEP land. And when you delete the root segment, those SDEP segments becomes the orphans, or we can say the logically deleted SDEP segments. And IMS pre-allocated these SDEP CIs for the each and every sharing partner in a sharing environment, and we call them as PACIs, which is pre-allocated SDEP CIs. And the short form is most of the people call them as PACIs. Okay, this is the diagram that depicts the PACIs. So again, this is your physical start of the STEP section. This is the physical end of your STEP section. This is the logical begin of your STEP, and this is the logical end. And these are the PACIs. So let's consider that there are 3 IMS subsystems. And for the example that we are going to refer later on, let's consider for simplicity, there are 3 IMS systems, 1, 2, and 3. And IMS subsystem 1 is catering the requirements of the Yukon region. IMS subsystem 2 is catering the requirements of, let's say, California region. And IMS subsystem 3, let's say, catering the requirement for New York region. So it is possible that the Yukon IMS might be dealing with the less traffic because there is less update, but California and New York subsystem might be processing more traffics and they will be doing more inserts. So in that case, this PACI will not be allocated, will not be utilized at the same pace compared to the PACIs which is allocated to New York and the California subsystem. And this poses some problem which we are going to talk about in next few slides. Okay, so before scan and delete, this is how it looks. You have the logical begin and you have the logical end. And when you run the scan, it will basically scan everything from the logical begin to logical end. But when you run the delete, there is a subtle difference here. Your logical begin cannot advance to logical end. As we have seen in a single IMS case in the previous slide, your logical begin was pointing to the logical end after the scan and delete. But once you have the PACIs for in a different in a data sharing environments, and when you run the scan and delete, there is a possibility that this logical begin cannot go beyond this point. And we are going to talk about that situation, why when which particular situation that might happen and how to resolve it. But there is a possibility that when you run the scan and delete, your logical begin is only advancing from this to this, and there is a lag between the physical delete and the logical delete that happens in the STEP section. Okay, so just hold on. We are going to talk about this situation with few more diagrams after a couple of slides, I guess. So, but before jumping onto that, there are a couple of things I wanted to cover here. There is something called STEP physical and the STEP marker segments. As Tom was mentioning earlier, some application might not be scanning from the beginning till end. They might be scanning of certain routes, which is holding a special STEP marker segments. So there are a lot of applications which might not be processing 24/7. They might be processing, let's say, days worth of data, maybe let's say at the 6 p.m. in the evening. They do the processing and then they do the journaling activity at 6 p.m. every day. So they are not operating 24/7, but they are doing some processing maybe at the end of the day. And for certain type of application, they can use STEP marker segments. So you will have a special field in the somewhere in the root segment, and off of that root segment, you will basically chain all those STEP marker segments, so that you will remember, okay, this is the root segment and this is the field from where I can do the scanning. So you will dedicate certain root segment with a special field in that root segment, under which you can insert the STEP marker segments. And when you want to scan, again, the STEP scan utility has certain unique keywords like start root, stop root, and you can specify the root segment there, which is holding this marker segments. And instead of reading from this logical begin to logical end, it will read between those two marker step segment, which is inserted under those special root. And it is of paramount importance that when applications are dependent on such kind of step segments or special marker segments, the physical order of your step segments are preserved. Because if you are doing some kind of maintenance, and if the physical order of your steps are not preserved, then scanning using the step markers is not going to provide you the correct results. So step physical is something which is of paramount importance if you are using a lot of step marker segments, which is the case with a lot of big shops these days. When these applications are designed several years ago, they have decided to go with the step marker segments. Okay, so there is something called quit CI processing, which is applicable to also to your step scan delete utility. I was explaining a situation earlier. Let's say you have three IMS 1, 2, and 3, and IMS 1 is catering the needs of Yukon region, IMS 2 is catering the needs of California, IMS 3 is catering the needs of New York. So there is a possibility that the activity or the frequency of updates on the Yukon region is quite less compared to what kind of traffic you are getting on the New York and the California region. So basically, when you specify quit CI processing on the scan and delete, it specifies that all the IMS partners will give up their current SDEP CI and any pre-allocated SDEP CIs immediately. This option is useful if there is an IMS partner that processes a low volume of transaction, therefore takes an extended period to fill its pre-allocated CIs. So in those situations, you can use something called quit CI processing, which is another control card on your scan and delete utility. And that will force your sharing partners to basically give away their pre-allocated SDEP CI and harden those updates on the DST, so that scan and delete won't suffer with that problem of logical begin not being advanced to the logical end, because basically there is an step segment in IMS1 from the Yukon region which is not allowing the step logical begin to go beyond that particular RBA. So let's talk about another feature that IBM or IMS has introduced very recently. I am saying recently because it is comparatively recent, because now we are talking about IMS 14 and not IMS 6. So this was the concept that was introduced in IMS 14, which is called automatic step buffer management. So we have talked about the situation and imbalance in the workload among IMS that are sharing steps can prevent step CIs from being physically deleted and fill up the area. And users may be unable to physically delete the specified step CI because of the low activity IMS. So IMS 14 allows the step CIs to be automatically cleaned up on a regular basis based on the certain frequency you are going to set at the IMS level. So these are the benefits you are going to get with the automatic step buffer management feature that was introduced in IMS 14, that it will allow the logical begin RBA to advance in order to free up the step space used by the next delete job. It will reduce the physical delete lag from the logical delete lag, and it will automate the manual processes, because in that case you might utilize some tool or some automated operations to see if your step space is not getting wasted. And in certain situation you might need to DBR the area to flush those step CIs. So all these problems can be eliminated with the help of something called automated step buffer management. Okay, this is the diagram which basically I've stolen from one of the IBM documentation. So let's consider again three IMSs, IMS 1, 2, and 3. IMS 1 is catering the needs of Yukon region. IMS 2 is catering the needs of California region, and IMS 3 is catering the needs of New York. So you have these packies which are allocated to these IMS 1, 2, and 3, and you have the logical begin here and logical end here. So let's say on the Monday morning, there is a credit transaction comes on the Yukon region, and it will be stored here, and it will be having a timestamp of Monday morning. Then a lot of transactions came on California and New York IMSs on Monday, different times, and they are basically stored here like this. Then on Tuesday, there is one transaction which is the debit transaction which came on the Yukon region, and you have stored that transaction detail here. And now you want to journal that activity, and you want to run the scan. So you can scan it, and it will scan all the data from logical end to logical begin to logical end. But when you run the delete, now this pre-allocated SDEP CI has an SDEP segment which is inserted on Tuesday, and that has a timestamp which is greater than all the timestamp of the SDEP segment which is inserted on Monday on this Yukon IMS, and on Monday on this California and New York IMS. So because of this SDEP segment, although there are only 2 transactions compared to several transactions on New York and California, but since this transaction happened on Tuesday, which has a timestamp greater than all the transaction happened or all the SDEP segments inserted on Monday, your SDEP logical begin basically cannot advance this point. And in that case, although your SDEP segments from here to here are logically deleted, they are not physically deleted because this much space is vested in the SDEP section. And it is possible that this type of situation keep accumulating, and it will waste a lot of your SDEP land, especially in a sharing environment when you are dealing with the packies. So it is always advisable, and I think most of the shops, they use a quit CI parameter with their scan and delete, and that will ensure that these SDEP CIs are hardened to DAST, and when you run the scan and delete, that will basically move the logical begin to the logical end, and this type of lag between the logical delete of the SDEP segment and physical delete will not be there, and it will not waste your storage in the SDEP plan, because when this situation accumulates, there is a possibility that your SDEP portion keep wasting space, and eventually you might run into FS status code, which nobody wants to see in today's world of 24/7. Okay, so
can I just clarify something, because I think
yes,
you just I think you faded out for about 5 seconds just before, but you were explaining about so if you do your scan delete with a quit CI in it, then that will mean that there'll be more efficient space being freed up there with the packages involved with those 3 IMSs.
Right.
Is that right?
Right. So one option is always using quit CI processing, and that's something most of the customer I've seen are using quit CI on their scan jobs. But this automatic SDEP buffer management concept, which was introduced with IMS 14, you can use certain parameters at the proc live level, which is again at the IMS level now, by which you can set certain frequency and the time of the day at which quit CI processing will automatically happen.
Sure.
But again, that is something you cannot control at the database level or the area level. That will be done at the IMS level. So there is not much granular control over there. But this is something a feature which was introduced by IMS, I think, based on certain client request, and obviously because these kind of situations are not easy to figure out in lab for IMS, and this was something which was detected in a real world, and some customer requested this feature, and that is why IMS Lab has came up with this feature. Although I'm not particularly sure if this is something which is very famous or used by a lot of customers, because I think most of the customers, they are more comfortable with using quick CI processing and having a control at the database level or the area level, as
Sure.
opposed to defining these parameters on the IMS level.
Yeah, so it sounds for some people it might be applicable to use the automatic SDEP buffer management in their shop, but
Right.
yeah, as you said, I think
not all.
Not all. So that's why quick CI is still a good way of doing it. I mean certainly we do quick CI,
Right.
But yeah, that could be applicable, the automatic SDEP buffer management, if it's applicable to your shop. Thanks.
Thank you. Okay, so we were talking about automatic SDEP buffer management concept, and your SDEP CIs may be unable to physically delete it because of the low activity IMS, that is Yukon. So it will have the performance impact and the shortage of the available SDEP storage. And the task that you won't be able to perform is physically advance the logical begin RBA to free up those SDEP space for those packies for your New York and California regions, and it will eliminate how your physical delete lag from the logical delete lag, because logically it is being deleted, but the physically your those things are not deleted upfront. So it will basically help you to do a SDEP buffer cleanup, which will happen automatically. A quit CI process will be done automatically. Each sharing IMS will clean up their own SDEP CIs. And when this happens, this automatic SDEP buffer management happens, messages are issued every time on the respective IMS to indicate that this process is being going on, it is being completed. And it basically generates a similar type of log records that any process might be doing a quit CI processing under the covers, like scan is doing with the help of keywords. Some of the BMC utilities under the covers, they do quit CI processing to make sure those updates are hardened to testy. So basically, to enable this feature of automatic SDEP buffer management, there are some keywords provided by IBM, which can be provided in the DF SDF XXS member of your IMS region. And these are different parameters. You can definitely go on this link and read about this. But these are the 4 primary keywords, which is SDEP auto, which will take either yes or no. So whether you want to use that feature or not, by default it is no. And then you can say SDEP EXP, which is the age. You basically specify if your SDEP segments uh, are aged to a certain time, they would automatically be cleaned up. Then there is something called frequency, number of times in a day you might want to pop up that timer, and you can specify the time of the day, which will be a single occurrence on that particular time. Automatic SDEP buffer management will happen automatically. So this obviously has couple of restrictions. Your area must be online. It should not be in the DBR status, and your buffer management will only occur if there is no other utility running against an area at that time. Because this will acquire and lock, and lock will only be acquired if there is no other utility running against that area at the same period of time. Okay, so let's move on to the small demo which I wanted to cover, that will give a good overview of how SDEP segments are being wrapped. So let me move on to the mainframe. Okay, let me know if you can see my screen on the mainframe.
Yes, indeed, really clear.
Okay, so let me explain what we are doing here. So we have basically DBR'd the area. So we are just doing some setup steps here. So we have DBR'd the area. We have done some DBRC notification. We have done the delete define of the database and the area. Then we have recovered the area from the image copy, and you can ignore these steps, and then we have started. So this is just to level set everything. You have restored the area from the image copy, and you have started the area, and then you have ran the online analyze, which is the base analyze, where we will see that the SDEP segments were in unwrapped state to begin with. Then after the online analyze, we have ran the SDEP delete utility. So what this delete utility will do, it will basically move the logical begin to the logical end. Then you are going to insert some SDEP segments using this method. So this is a homegrown BMC utility to simulate some updates to the database, which is similar to DDLT0 that IBM provides, where you can do the updates without having the actual application program. So there are two IMSs here, IMS F15P and F15S. So we are talking about two IMS, two sharing partners. So we did some SDEP inserts from the primary IMS, and then we did some SDEP inserts from the secondary IMS. So basically what we did here, we did the delete. So now your SDEP begin will point to the SDEP logical begin will point to the SDEP logical end. And then we started inserting the SDEP segments from primary IMS and secondary IMS. Then after that, we have again deleted. So again, your SDEP logical begin will move to the SDEP logical end further down in the area. And then we further add the SDEP segments from the secondary IMS and the primary IMS. And then we again delete the SDEP segments. So why we are inserting and deleting is to move your SDEP logical begin and end towards the end of the area. Because at some point we want the SDEP segments to be wrapped around and move into the upper portion of the SDEP section. So again, we are doing some inserts from secondary and primary, and then we have done the delete, and then again we have inserted from primary and secondary, and then we have ran the online analyze. So after doing these many inserts and deletes, your SDEP segments are finally in the wrapped situation. So let me first show you the analyze one, which is the base analyze here when we started the area. So this is analyze 01. So let me go into the analyze. So this is nothing but a pointer checker utility from BMC, which can show you certain important RBAs in terms of your SDEP section. So you can see that this is the sequential dependent portion, and this is the SDEP logical begin and logical end. So this is the cycle count, which is 1. And this is the logical begin RBA, and this is the logical end RBA. So your logical end RBA is greater than your logical begin RBA. And this is your physical SDEP CI, first SDEP CI, and this is the end of the area. So this logical begin and logical end basically lies between these two RBAs. So in this situation, the SDEPs are not trapped, and let's look at how many SDEP segments were there in the baseline analyze. So there was 751 SDEP segments present in this area. And post that, we have done these 4 different deletes. So you can see that we have deleted, inserted and done the delete, inserted and then done the delete, and then inserted and further done the delete, and then further inserted via this simulators or the simulation of the update or the insert activity for SDEP from 2 different IMS, where we have inserted this segments, and this basically tells, okay, this is the SDEP segments, and this many segments are inserted and this many bytes are inserted. So post that, we have ran the analyze again in the last, just to see, okay, how after doing this kind of deletes and insert, how your SDEP segments are looking like. So if you go and look at this analyze report, which is done doing all the update activities and the delete activities, you can see that this is your SDEP portion, and now you can see this is the logical begin and this is the logical end. Now the cycle count is different. In the analyze 1 report, the cycle count was same, but in the analyze 2 report, now your cycle counts are different, which means that your SDEPs are now wrapped. So you can see that this is the logical begin RBA and this is the logical end RBA. And this RBA is less than this RBA, which means the logical end now resides above the logical begin, and your SDEPs are in wrapped situation after doing a lot of inserts, doing scan, delete, and then doing a lot of inserts, doing scan and delete. If you go back and look at this slide, so we have done a lot of inserts from here to here. Then we have done the delete. So now logical begin points to logical end. Then again, we have done a lot of inserts. So we have done the inserts here. Then we moved did the delete, which basically moved the logical begin to logical end. At one point, step segments were filled till here, and now started flowing in this upper portion of the step section, and that is when your cycle count moved from 1 to 2 in the step pointers. And the logical and RBA will basically the logical and RBA would be a lower value than the logical begin RBA, because the RBA of the logical begin would be a value which is greater than this, as you can see in this report. So again, your first SDEP CI is same, which was there before with the baseline analyze and the end of area. But after doing those scans and deletes and inserts multiple times, eventually your SDEPs are wrapped, and your logical and has a different cycle count, and its RBA is less than the RBA of your logical begin. So your SDEP segments will be wrapping around multiple times, and it is possible that this number would be a very big number, which means that your SDEP segments are wrapped that many times. And maybe after some time you might do some maintenance where you delete your areas and recover it, or maybe do some kind of unload and reload, and that time it will be reset again to 1 and 2. So this 2 indicates that it is only wrapped once. It could be very higher number, but the difference between these two is always going to be 1. Okay, so I think with that I will take it as I think I've covered everything what I wanted to cover in session today. And these are some of my details from BMC software. You can always reach out to me via these emails if you have any outstanding questions. I would be happy to talk on the SDEP segments. They are always unique and they always fascinate me. And with every new problem I work on, I find something new related to the SDEP segments. And it's very special within the FastPath, because FastPath database itself is very unique in terms of IMS, but the SDEP segments are even more unique. And as I mentioned earlier with an example, that it is a special parking lot for VIPs and VVIPs. So you can always remember that analogy. And so with that, I will open it up for the feedback. So please go to this link, or you can scan this QR code. The session code is 5N, and you can provide the feedback. And we are always doing some constant effort to make sure how we can deliver these presentations better, so we can attract more audience in IMS. And this is the same presentation I've covered in the GAC in-person conference in the November last year. But I wanted to repeat it so that it can reach more audience, and I'm pretty sure this time it is recorded. So definitely there will be a lot of people later on who can refer to the recording and maybe able to at least get something which they are not aware of. And obviously we can have more discussions, deeper discussions on these topics. So with that, Dom, I will hand it over to you, or if there are any questions, and if the time is left, we can take it now, or we can always answer them offline later on.
Yeah, sure. Many thanks for that, Anshul. And yeah, we've got a couple of minutes left. So if anybody does have any questions, then please don't be shy. Please feel free to ask those questions now. You can just unmute. You just have to make sure you unmute yourself, because I've enabled that to happen. So please unmute yourself and ask that question. In terms of the presentation, thank you very much for that. I thought that was really good, and it's brave of you to actually go to the screens if you're logging on live as well, looking at your your shop. So in terms of doing that, those utilities that you showed us then, and another thing to mention is that you've diligently put these slides on the available to all. So basically, if anybody just goes onto the agenda and goes on this particular for the session, so this session was 5N, and we basically, you can click on the link by just clicking on the agenda N50 5N, and then what you'll do is you'll just have to sign in for your so that you get your personal agenda, and then you'll be able to download the slides onto your PC. So that's also available. And as Anshul's saying, these are recorded, so in a few days' time, once they've been edited, then those will be available. The videos will be available again on the website using the method I've just described, going on to the agenda and then pointing to the video. And those videos will be available for a year, and apparently they even get onto YouTube after 1 year. So you'll be famous for a bit. So have we got any more questions then? We've got it's coming up to just the top of the half hour. So any more final questions? I mean, I'd just like to say there was one clarity point right at the beginning where you were mentioning about the if you were the number of the CIs that you'd be pointing to if you were the randomizer, and then you would be placing, you know, your number plate. And if that had Yukon, it would go to the Yukon CIs. And I just, all I was going to say was, it's a very, very minor point, but obviously you can have a randomizer which will specify which area. If you've got more than one area on your database data set, you might also, it might then go to the first CIs in that area. So it might be that you have 2 or 3 areas, and that the randomizer has pointed you to a specific area and then done what you've said, which is do the number of CIs. It might have gone to the first numbers of CIs in that area. So there is, you know, we can have a 1 area database with the randomizer, and we can also have more than 1 area.
In fact, with the recent IBM announcement, there could be up to 10,000 areas in a single database.
Okay, wow, yeah, excellent. Yeah, they keep on upping it, don't they? The limit, because there's loads of people out there that want more than that. What was it? That was 2048 was
2048 was the previous limit.
Was the previous limit, wasn't it? Yeah, excellent. So just any more questions, then just ask via unmuting yourself. But I'd just like to say thank you very much. So it doesn't look as though we've got any more questions, but the foils are available, and the slides and the videos are available as well in due course. So I'd just like to say thank you very much for your attendance, everybody. We've had about 80, 90, we've nearly had 100 people on the sessions for IMS, the 8 sessions that we've had over the last 3 days. And this is the final session for the IMS stream. But I'd just like to say thanks everyone, and please, your feedback is important. So if you could fill out that, I think there was a QR link before, but its session is 5N for that final feedback. Thanks everybody. Have a good rest of your virtual conference. There are still other sessions not in IMS still happening today up until about 5 or 6 p.m. tonight, so UK time. So thank you very much for your active attendance, and thank you, Anshul, for giving us that informed presentation. Very good. I thought it was excellent. Thank you,
Dom, for hosting all these sessions in the IMS stream. That's really appreciable.
Okay, no problem. Thank you very much. And with that, I'll hand you over to have a good rest of your day, everyone. Thank you.
Thank you, guys.
Thank you, everyone. Have a good day. Bye-bye.
Cheers.